Hello everyone. This is another circuit synthesis example. This example is construct a circuit diagram for following LC impedance function using first Cauer form. There are two Cauer forms, first and second. I use same example for both the Cauer form, first and second Cauer form. This is the impedance function of a LC network. The numerator has s to the power 4 plus 4s squared plus 3, and the denominator s to the power 3 plus 2s. Before construct the circuit, we have to check some properties of this impedance function, and these are the general properties of a passive RLC function. There are 6 properties. Now we will consider one by one. The first property says must be a rational function in S with real coefficient. You can see this is a function with S and it has real coefficient. Then first condition is satisfied, and second one is may not have poles or zeros in the right half S plane. For this one we have to find poles and zeros. For that one, for the poles, we can obtain poles from the denominator. I rewrite the impedance function with roots. We can write s to the power 2 plus 3 square plus 1 over s times s square plus 2. These are the roots. Then for the poles, we can obtain from the denominator. There are three poles s equal 0 and s equal plus or minus root 2j. These are the poles of this impedance function, and zeros we can obtain from the numerator. There are 4 zeros. This is equal plus or minus root 3j, and is equal plus or minus j. Then we can plot these poles and zeros in the complex S plane. This is real axis and this is imaginary axis. There are 3 poles at the origin and at plus root 2 and minus root 2. It is around 1.4. Then there are 4 zeros at plus 1, minus 1, plus root 3 and minus, this is a dot. Then according to the second one, may not have poles or zeros in the right half S plane. This is the right half S plane. You can see there are no any poles or zeros in the right half S plane. Then second property also satisfied. And third one is may not have multiple poles or zeros on the j omega axis. You can see there are no any multiple poles or zeros. Then third one is okay. And the fourth one is may not have the degree of the numerator and denominator differing by more than 1. For this function, degree of the numerator is 4 and the degree of the denominator is 3. The difference is 1. It is not more than 1. Then fourth one is okay. And fifth one is must have non-negative real part for all s equal j omega. For that one, we have to assign s equal j omega for this function. So del c function is x to the power 4 plus 4s squared plus 3 over s to the power 3 plus 2s. Now I can assign s equal j omega 4 plus 4 into j omega squared plus 3 over j omega to the power 3 plus 2 j omega. From this one, omega 4 minus 4 omega squared plus 3 and the denominator j times 2 omega minus omega cube. You can see the denominator is a imaginary part, then real part of del c j omega is equal to 0. Then it is a non-negative. Then fifth one also satisfied. The last one is must have positive and real residues for all poles. For that one, we have to calculate the residues. For that one, we have to do the partial fraction expansion for this impedance function. Say del C is equal to x to the power 4 plus 4 squared plus 3 over s times squared plus 2. These are the poles. Then expansion we can write as plus b over s gonna c s plus b over s squared plus 2. For this one, the degree of the numerator greater than the degree of the denominator. Then we can write as plus bos plus cs plus d over s squared plus 2. Now we have to find what the value of a, b, c and d. S squared plus 4s squared s to the power 4 plus 4 squared plus 3 is equal to s times s to the power 3 plus 2s plus b times s squared plus 2 plus s times cs plus d. For this one, I first consider the s to the power 4. From the left hand side, value is 1. From the right hand side, it is equal to a. The value of a is 1. Now I consider s to the power 2. From the left hand side, value is 4. From the right hand side, 2a plus b. From this one, 2a. From this one, b plus from this one, c. We know the value of a, then it is equal to 1. 2 is equal to b plus c. Then I consider s to the power 1. From the left hand side, no any s terms. From the right hand side, it is equal to d. the value of d is equal to 0. Then I consider s to the power 0 from the left hand side, value is 3. From the right hand side, value is b, 2b. The b is equal to 3 over 2. From this one, we can get the value of c. 2 minus 3 over 2 is equal to c. Value of c is half. Then partial fraction expansion is value of a is 1, s plus value of b is 3 over 2, os plus value of c is half over square plus 2. These are the residues. This one, b and c. You can see both are positive and real. Then last property also satisfied. Must have positive and real residue for poles. Then there are some additional properties for passive LC driving point function. The first one is function must be a ratio of even or odd even polynomials. You can see in this one, this function, when you consider the numerator, these values are even. So this one is to the power 0, even values. And from the denominator, s to the power 3 and s to the power 1. These are odd terms. Then function is even or odd. Then this one is satisfied. And second one is poles and zeros lie on the imaginary axis and are simple. You can see all the poles and zeros are lie on imaginary axis and all are simple. There are no complex one. Then second property also satisfied. Third one is the highest power of the numerator and the denominator should differ by unity. And the lowest power of also should be differ by unity. The highest power of the numerator is 4 and the denominator 3. The difference is 1. This is highest. When you consider lowest from the numerator, the lowest one is 0. Denominator, lowest one is 1. Difference is 1. Then third property also satisfied. And fourth one is there must be a pole or 0 at the origin and infinity. You can see there is a pole at origin. The fourth one is okay. And last one is the poles and zeros alternate. In here you can see pole 0, again pole, again 0. Then last one also satisfied. Now we can do the Cauer forms. First and Cauer form we have to apply for this function. In Cauer form, we are using continuous fraction expansion. I'll first do first Cauer form. First one, the numerator is s to the power 4 plus 4s squared plus 3. And the denominator is s to the power 3 plus 2s. In here, you can see degree of the numerator is greater than the degree of the denominator. If I divide this numerator by denominator, we can obtain s to the power 4 plus 2s squared 0 plus 2s squared plus 3. Now I can use this function here s cube plus 2s. From this one, I can obtain s over 2 s cube plus 3s over 2. From this one, 0 plus s over 2. Then this term, I can use this in here, 2s square plus 3. For this one, 4s, 2s square, 0 plus 3. Then s over 2, we can use here s over 2. From this one, s over 6, s over 2. The remaining part is 0. In here, this is the impedance function. Then first value is impedance value. Second one is admittance value. Third one again impedance. And final one is admittance value. When we consider an inductor with the value of L, the impedance value is Ls and the admittance value is 1 over Ls. When we consider a capacitor, impedance of the capacitor is 1 over Cs and the admittance of the capacitor is Cs. We can use these terms for find what is a inductor and what is a capacitor. If we consider this Z1, my name is as Z1, Y1, Z2 and Y2. For this Z1, it is like to a inductor with the value is 1. And second one, it is equal to a capacitor. Value is half. And third one, it is again inductor. Value is 4. And the final element is again a capacitor. Value of 1 over 6. Now we can draw the final circuit. First, impedance value. That means the inductor is connected in series. 1 Henry. This is L1. And second one is admittance. It is a capacitor. Connected in parallel. Value is 1 over 2. C1 is 1 over 2 farad. And third element is again inductor. L2. Value is 4. And the final element is the capacitor connected in parallel. C2. Value is 1 over 6 farad. This is ZLC. We can obtain from these 2 points. This is the final circuit that we can obtain by applying first Cauer form for this impedance function. Then second part is I will apply the second Cauer form. Second Cauer form. For this one, I have to rearrange the function in an ascending order. Then the numerator will be 3 plus 4s square plus x to the power 4 and the denominator 2s plus x to the power 3. From the first Cauer form, we use the descending order. Power of s, we have to arrange in the descending order. You can see s to the power 4, 2, and 0. In the second Cauer form, we have to arrange it as a ascending order, s to the power 0, 2, 4. Then we can apply the continuous fraction expansion. 3 plus 4s squared plus s to the power 4, 2s plus s to the power 3. From this one, 3 over 2s, 3 plus 3s squared over 2, 0 plus 5s squared over 2 plus s to the power 4. This term 2s plus s to the power 3 value is 4 over 5s, 2s plus 4s squared plus 4s cube plus over 5. 0 plus 1 over 5 s cube. This term 5s squared over 2 plus s to the power 4. 25 over 2s. 5s squared over 2. 0 plus s to the power 4. This one 1 over 5 s to the power 3. This one 1 over 5s. 1 over 5s cube. Final answer is 0. From this one, this is impedance one. This is admittance function, y1. Again, impedance is Z2. This one again, admittance value. To find what are the elements, whether it is inductor or capacitor, we have to refer these values. If I consider the Z1, it is more like to capacitor. It's a capacitor. Value is 2 over 3. And when I consider the Y1, it is an inductor. L1 value is 5 over 4 Henry. And the third element, it is a capacitor. Value is 2 over 25 farad. And the final element is inductor. L2 value is 5. Now we can draw the final circuit. First element is a capacitor. It is connected in series. Value is 2 over 3 farad, C1. The second one is admittance. Inductor, it is connected in parallel. L1 is 5 over 4 Henry. Third element is another capacitor, C2, 2 over 25 farad. And the final one is inductor, L2, 5 Henry. This is the final circuit that we can obtain by applying the second Cauer form. Series connected capacitor and parallel connected inductors. In first Cauer form, we can obtain series connected inductors and parallel connected capacitors. And this is the final circuit from the first Cauer form, and this is the final circuit from the second Cauer form. I hope you all are clear about this example. Thank you.